Hello everyone, I am Ashwin, Assistant Professor in the Department of Civil Engineering, PESCE College of Engineering, Mandya. In this lecture, we will understand what is moment of inertia, parallel axis theorem, perpendicular axis theorem, and some other relations. The property of matter by virtue of it to resist any change in its state of rest or of uniform motion is called inertia. The product of the area and square of the distance of center of gravity of the area from an axis is known as moment of inertia, and it is represented by I. Now let us consider a plane lamina of area A as shown in this figure. Let x be the distance of CG of area A from axis OY, and y is the distance of CG of area A from axis OX. Now the moment of area about axis OY is given by area into perpendicular distance of CG from OY, that is AX. So if you want to take the moment of area of this particular plane, that is this area into perpendicular distance of CG. Now this is the perpendicular distance, that is x is the perpendicular distance for this area. Now that's why it is A into x. Now from this equation 1, it is known as first moment of area about axis OY. If the moment of area is given as given in equation 1 is again multiplied by the perpendicular distance between CG and axis OY, then the quantity becomes AX into x or AX square. Now this is known as moment of area or second moment of area or area moment of inertia about axis OY. Now also the area can be replaced by mass. Sometimes we will also represent it with respect to mass, and similarly we can replace area and we can introduce mass there. In that case it will be moment of mass or second moment of mass or mass moment of inertia. Now let us understand this parallel axis theorem. It states that moment of inertia of a given area about any reference axis, say AB, is equal to the sum of moment of inertia of area about its centroidal axis ICG and the product of area and square of the distance between reference axis and centroidal axis, that is H. So it is understood better by this expression here. So IAB is equal to ICG plus AH square. Now IAB is the reference axis, moment of inertia about any reference axis, that is IAB. Now it is equal to sum of these two terms, that is ICG and AH square, sum of ICG and AH square, where A is the area and H square is the distance between reference axis and centroidal axis. Now consider an elemental area dA at a distance of say y from the centroidal axis, and as shown in this figure. So from the definition, moment of inertia about axis AB, which is parallel to CG, is given by dA into y plus h whole square. Therefore moment of inertia of entire area is given by summation of dA into y plus h whole square. Now simplifying this, we will get also we know that summation of dA is equal to A, and summation of y square dA is equal to ICG. Now putting all this and simplifying, we will get IAB is equal to ICG plus AH square plus 2h into summation y into dA. But also the distance of CG of the total area from the x-axis is 0 in this case. So that's why summation of y dA will be equal to 0. Now on simplifying, we will get IAB is equal to ICG plus AH square, which is the parallel axis theorem. Now let us understand perpendicular axis theorem. So If Ixx and Iyy be the moment of inertia of a plane section about two mutually perpendicular axes xx and yy in the plane of the section, then the moment of inertia of the section Izz about the axis zz perpendicular to the plane and passing through the intersection of xx and yy is given by Izz is equal to Ixx plus Iyy. So the above equation is also referred to as polar moment of inertia. Now let us consider a plane section of area A as shown in this figure. So let OX and OY be the two mutual perpendicular axes. Now consider a small area dA. Now let x be the distance of dA from axis OY and y be the distance of dA from axis OX and r be the distance of dA from axis OZ. Now we can say that from the figure r square is equal to x square plus y square. Now the moment of inertia of dA about x axis is given by dA into y square, that is from the parallel axis theorem. Now moment of inertia of total area about x axis is given by summation of y square into dA. Now similarly moment of inertia of total area about y axis is given by x square into dA, and similarly moment of inertia of total area about z axis is given by summation of r square into dA. Now substituting the values for Ixx, Iyy, we can say that Iz is equal to summation of dA square x square plus summation of dA into y square, and also again substituting that back, we can say that Izz is equal to Ixx plus Iyy. This is perpendicular axis theorem. Now let us understand the next concept, that is radius of gyration. Radius of gyration of a body about an axis is a distance such that its square multiplied by the area gives moment of inertia of the area about the given axis. Now let us consider this plane, and from the figure the moment of inertia about the given axis, this is the given axis, can be written as I is equal to A1, that is area, into R1 square from parallel axis theorem again, plus A2 into R2 square plus A3 into R3 square plus etc. Now let the whole mass or area of the body concentrated at a distance k from the axis of reference. Then the moment of inertia of the whole area about the given axis will be equal to ak square. Now if ak square is equal to I, then k is known as the radius of gyration. So if we simplify for k, we will get the expression for k as square root of I by a. Now in the next section we will try to determine the moment of inertia of some standard sections. So some of the very important sections which we have to learn are rectangular section. Again we will have three cases here. Moment of inertia about x axis passing through CG of the section. Similarly about y axis, moment of inertia about y axis passing through CG of the section, and about the base. So again for hollow rectangular section we can determine the moment of inertia. Similarly for triangular sections, circular sections, hollow circular sections. Again there are still a number of sections available, but these are very important ones which we have to learn. Now we will understand how to determine the moment of inertia of a rectangular section. That is, in the first case, moment of inertia of rectangular section about xx axis passing through the CG of the section. Now this figure shows a rectangular section A, B, C and D having width equal to B and depth is equal to D. Now let xx be the horizontal axis passing through the CG of the rectangular section. The moment of inertia of the given section about xx axis is represented as Ixx. Now consider a small elementary strip of thickness dy at a distance of y from the xx axis as shown in this figure. Now the area of this strip is equal to b into dy. B is the width of the rectangle and dy is the thickness. Now moment of inertia of this strip about xx axis is given by b into dy into y square, that is area into centroidal distance square. Now the moment of inertia of the whole rectangular section can be obtained by integrating the above equation from the limits. So if you take this as the x-axis, so this is minus d by 2 and this is plus d by 2, correct? So that's why we have to integrate between minus d by 2 to plus d by 2. Now representing that and applying limits, we will, once you simplify, you will get ixx as b d cube by 12. So in the second case, so we will consider the axis in the yy direction. So moment of inertia of rectangular section about yy axis passing through the CG of the section. Now again consider the same rectangular section, but you are considering the elemental strip in the vertical direction, and the distance between this yy axis to the elemental strip is x and the thickness of the elemental strip is dx. Now again the area of the strip will be equal to d into dx. Moment of inertia of area of strip about yy axis is equal to area into distance square, x square. Now if we want the moment of inertia of entire section, we have to integrate between the limits minus b by 2 to plus b by 2, and integrating and solving and also applying the limits, we will get Iyy as db cube by 12. So similarly we can also determine the moment of inertia of different sections from the first principles. Thank you.